Here's how to assess the normality of data. Some statistical models assume the data are randomly selected from a normally distributed population. This is called the normality assumption. In this video, I show you how to use graphs to evaluate whether it's reasonable to conclude the data are a random sample from a normally distributed population. This is a somewhat subjective process. You use personal judgment to form a conclusion. Slight departures from normality may not be too serious, because most statistical tools are very robust to departures from normality. Sometimes departures from normality can be corrected by transforming the data. For example, you could try taking the square root or the logarithm of the data and check to see if the transformed data are more normal. In this video, I used 4 examples. 2 examples are 2 different random samples from the same normal population. These examples will show you what to expect when the normality assumption is true. The 3rd and 4th examples are not from normal populations. The 3rd example is from a beta distribution, and the 4th example is from a t-distribution. I'm going to use histograms and QQ plots to evaluate normality. Here's the R code used in example 1. I'm going to explain the purpose of each line of the code. The first line starts with a hashtag. Anything on the line following a hashtag is ignored, so it's simply a comment. Comments should be used to explain what you're doing. It's helpful when you go back to the same code you wrote a few weeks ago to remind you of what you were doing and how you did it. In line 2, the setSeed function controls the random selection process. If you use the same setSeed number that I use, we should get the same results. In line 3, data equals R norm, parentheses n is 100, mean is 200, SD is 20, creates an object named data. And in this data, I'm going to store a random sample of 100 objects from a normally distributed population having a mean of 200 and a standard deviation of 20. The next line, HIST, open parenthesis data, constructs a histogram of the data. The QQ norm data line in the code creates the QQ plot, and the QQ line data adds a line to the plot. Here's the histogram. Visually, you can see that it's approximately symmetrical and bell-shaped, and that's what you should expect if the sample is from a normal population. It's not exactly symmetrical because of random sampling. A second sample from the same population would be a little different from this one. Here's the QQ plot. If the sample is from a normal distribution, the observations in this plot should fall on a line from the lower left to the upper right. The QQ line function adds the line to the plot. It helps you to see how close the observations are to the line. Example 2 is a second random sample from the same population. Notice that setSeed is different from the one used in example 1. Here's the histogram. Notice that it's not quite as symmetrical as the histogram in example 1. This demonstrates the fact that even when the population is normal, the histogram may be a little skewed one way or the other. On the QQ plot, the points fall roughly on the line, but there is some scatter around the line. The population is exactly normal in this example, so this plot demonstrates the fact that the data may not form a perfect straight line pattern even when the normality assumption is true. Example 3 selects a random sample from a beta distribution. The only thing you need to know right now about a beta distribution is that beta is a family of probability distributions. The beta distribution has 2 so-called shape parameters. When you change the value of the shape parameters, the shape of the distribution changes. This example uses 1 and 5 as the 2 shape parameters. This is the histogram of the sample from the beta distribution. You can see that it trails off to the right. This shape is called skewed right or right skewed. A histogram that looks like this is a pretty clear signal that the population is probably not normally distributed. The points on the QQ plot also tell you the population is not normal, because the points do not form a linear pattern from lower left to upper right. Transforming this data by raising it to a power, such as maybe the 0.25 power, might improve the normality. The fourth example uses a random sample from a t-distribution. The t-distribution is bell-shaped and symmetrical, but it's controlled by its degrees of freedom. With a small number of degrees of freedom, the dispersion is larger, it's more spread out than the normal distribution. When the degrees of freedom increase, the t-distribution converges with the normal distribution. In this case, we've got 20 degrees of freedom. Here, the t-distribution is not quite normally distributed, but it's pretty close. Here's the histogram, and as you can tell from the histogram, it looks pretty symmetrical. The QQ plot looks like it probably could have come from a normal distribution. So in this example, I don't think it would be a terrible mistake to conclude that the normality assumption was met. Keep in mind, this exercise was a situation in which we knew in advance whether the population was normal or not, and we looked at the impact of non-normal populations on the histograms and QQ plots. In real-world problems, we don't know the true shape of the population, so we use tools like these to help us evaluate the normality assumption. The simulation also demonstrated the set seed function. This creates reproducible research. I use this on some homework and test questions to create different data sets. Thanks for watching, and let me know if you have any questions.